All right. And since the last topic is going to be covered on Monday, I'll try to have a practice test ready fairly soon, perhaps by the end of the week or so, the practice final exam. Okay, so the idea for today and Monday is that we're going to consider how to solve Laplace's equation on certain domains of a singular circular nature. And it turns out that separation of variables that we've used for other problems will be helpful here too. So here's a problem under consideration. So Laplacian of u is 0. And we're going to solve it on disk of radius r tilde, so the domain satisfying this inequality. And turns out I'm going to need capital R with no tilde later on, which is why I have the tilde here. So r tilde indicates the size of our domain. And then on the circle of radius r tilde, that's the boundary of our domain. And so our boundary condition is that our solution u is equal to some given function g. Right? So it's equal to g on circle. It's Laplacian is equal to 0 inside. So since we're solving the PDE on the interior of the circle, and this is a Dirichlet type 1 boundary condition, so that's why this is referred to as the interior Dirichlet problem. We will see the exterior Dirichlet problem on Monday. Now, due to the circular nature of our domain, polar coordinates is a good idea. So this is the Laplacian in polar coordinates that was derived last time. So now we'll consider our polar variable r between 0 and r tilde. Notice that the Laplacian is not defined at the origin. And then our theta variable in polar coordinates 0 to 2 pi. And then our boundary condition is also described in terms of polar coordinates, that when little r equals capital R tilde, that puts us on the circle of radius r tilde, that's our boundary. And we think of g as a function of only theta. So now, this is a problem we're going to solve using separation of variables. So, similar to how we use separation of variables before, we assume that our solution is a product of a function of one variable times a function of the other variable. In this case, our variables being r and theta instead of x and t like we had before. So keep in mind notation, here we have capital R again, but with no tilde. So capital R, plain capital R refers to this function of our radial variable, whereas capital R tilde refers to the radius of our domain. So, as before, separation of variables. We take the form of our solution, substitute it into the PDE. So we have derivatives with respect to r. We're taking derivatives of capital R. Derivatives with respect to theta. We take derivatives of capital theta, theta. And we want to rearrange this equation so that we have a function of only little r on one side and a function of only little theta on the other side. So algebraically manipulating this, we wind up here, and that goal has been achieved. That This fraction depends only, it's a function of only little r. This fraction is a function of only little theta. That must be equal for all little r, little theta. Those are independent variables, so the only way they can be equal is if both are equal to a constant, k, that is the separation constant. Right. Yeah, it is the exact same way the separation of variables worked out before, but I figured the review is helpful because it's been a while. So now if I set this part equal to k, I get this second ODE, and then this fraction equal to k. So here are two ODEs that we get for capital theta and capital R. And we need to know for which values of k can there be a viable solution. Like before, we considered the cases of k being positive, negative, 0. First case, k equals 0. So focusing on the theta equation, the theta ODE reduces to capital theta double prime equals 0 if k is 0. So that means that capital theta would have to be a linear function of little theta. So something of this form. For some constants a and b describing the y-intercept and slope. But this function also has to be 2 pi periodic because we're dealing with polar coordinates. The periodicity is necessary to ensure its solution is continuous on the disk. But the only way a linear function can also be 2 pi periodic and also be a continuous function is if it's 0. Actually, sorry. Not the whole thing 0. The slope must be 0. Capital theta equals a constant function a. That is also permissible. So we have a solution in that situation. Positive k, then we have our ODE for capital theta would have a solution of this form, a combination of these exponentials. But again, we require 2 pi periodicity. And there is no non-trivial solution of this form that would make that possible. So we forget about that. And then finally, when k is negative, we can write k as minus lambda squared, where lambda is assumed to be non-negative. And we get a general solution of this form. Well, a combination of cosine and sine. And that certainly works. We just have to make sure this is 2 pi periodic, which will happen as long as well, for this case of k strictly negative, lambda, we require lambda to be a positive integer. All right. If we allow lambda to be non-negative, then that would also account for this case. As I mentioned earlier, that would produce at least a solution. So, to summarize, here are the possible solutions for the theta ODE. So we index them by n. So we have an cosine n theta plus bn sine n theta, where n is a non-negative integer. So that accounts for this case of negative k, and this case of k equals 0, where we have a non-zero value for this constant a here. So our separation constant is equal to negative any integer squared. So now we move to the other ODE, one for capital R. And I filled in here, well, actually, the previous ODE for capital R is right here. But I fill in k equal to minus n squared right here. And this is what we get, where n is allowed to be any non-negative integer. There's a well-known ODE called the Euler equation. Okay. Now, to solve this, if we get change of independent variable, z is natural log of r, then this ODE transforms into one that is a second order linear ODE of constant coefficients. Because right now, this one, you can't apply the techniques that you originally learned in your first ODE class for solving linear ODEs with constant coefficients, because coefficients are not constant. We have r squared here, we have r here. But by making this change of variable, do the following, that okay. So we're going to derivative the capital R dz that'll be equal to capital R to little r times z. And actually, I'm going to do this the other way. It'll be easier. Okay. So dz dr, of course, will be 1 over r. Okay. In other words, little r, capital R prime, is equal to dr dz. So this term right here reduces to a derivative of capital R with respect to z. And you get an idea that this would simplify also to become just a second derivative of R with respect to z plus other terms. So this gives you an idea as to how this ODE simplifies considerably once you make this change of variable. And I won't go through all the details of that here, but what we get from a solution, once we solve this simplified ODE of constant coefficients and then change variables back to our original independent variable little r, our general solution has this form. So little r to the n plus little r to the minus n. For some constants a and b, which will end up being determined by the boundary condition. Now, we're actually going to not include this term involving little r to the minus n. And the reason why is we want the solution to be well defined at the origin. But we have this here that we will be dividing by 0. So we only seek solutions of this form. And that's going to be enough to obtain a solution to our problem. So now, if you keep in mind what's happening to separation of variables, our solution is assumed to be our function capital R times our function capital theta. So now we have both of these. So if we multiply these two together, then we have a solution of this form. So here's our theta solution that I showed you earlier. And then we have little r to the n. And I've included this factor here, 1 over r tilde to the n. That's going to be convenient for determining the coefficients an and bn that will satisfy our boundary data. So you'll see in a moment why. I can multiply this by any constant I want. So I'm going to take a linear combination of these anyway, but this turns out to be a particularly convenient choice. So now, if I take all solutions of this form, for n equals 0, 1, 2, etc., then here I have my general solution. Now, in the case of n equals 0, well, this would reduce to a0, and this factor would just become 1. So we're just going to have a constant term up here. And we've seen before with Fourier series that we include a factor of 1/2. Again, that's just for notational convenience. So when you're solving, so this is keep in mind for your homework or a test. When you're given an interior Dirichlet problem, like I stated at the beginning, you can jump directly to this solution formula. But you know your solution is going to be in this form. It's just a matter of figuring out, filling in the proper value of r tilde, which comes from the radius of your domain, and finding the proper coefficients, a0 or a and bn, so that the boundary condition is satisfied. So that's the remaining task. So we evaluate our solution on the boundary. That means setting r equal to capital R tilde, which causes this factor to be 1. So that's why I threw that factor in here. So now we have this, and the solution must be equal to g on the boundary. So that's why I filled that in on the left side. So in other words, all we really need to do is find the Fourier series coefficients of our boundary data, g of theta. And here we have integral formulas for an and bn. But keep in mind how for certain problems this can simplify. For example, what if g of theta was equal to, let's say, cosine of 2 theta? Then you'd have a2 equal to 1, and all over AN and all BN would be equal to 0 in that case. So we can, that shortcut can happen on a problem by problem basis. If that doesn't apply, like for instance, what if g of theta is if it's some other periodic function that's not readily expressed in terms of sines and cosines, then you can use these integral formulas to get the AN and BN, the coefficients that you need. And that's it. So really, to solve this problem, all you need is this solution formula to get your AN and BN. Use these. Are there any questions about solving that? Now, here's another way of expressing the solution to this interior Dirichlet problem. If I take these formulas for AN and BN and substitute those general formulas into here, since AN and B, those formulas A and B are in terms of integrals, we can express the entire solution as an integral. Now, I guess for notational convenience, or we can also argue laziness, I'm going to use, since I'm not dealing with separation of variables anymore, I can use capital R to refer to the radius of a domain, or what you think of it as capital R tilde from before. So what happens is, in our general solution formula, you have cosine n theta, sine n theta. But once I include the formula for AN in here, cosine n theta will be multiplied by cosine n alpha. And similarly, sine n theta will be multiplied by sine n alpha. So that's what we end up with here. So now, our solution is 1 over pi times an integral from 0 to 2 pi of this series in square brackets times our boundary data. And what's convenient is this part can be readily condensed using a trig identity, cosine of n times the difference of angles, theta minus alpha. Now, cosine of any angle can be written as e to the I times that angle plus e to the minus I times that angle all over 2. Now, the reason why this is helpful is now I can write every term in the summation as something raised to the n power. So here I have little r over big R times e to the I alpha minus, the theta minus alpha, all raised to the n power. So I have that here. And then similar to the other term with a negative in the exponent. So I have that here. So now I have 1 plus this series plus this series. Now, the reason why this is helpful is because what we have here is a geometric series. Now, a geometric series is known to converge if and only if the expression being raised to the nth power in each term is less than 1 in absolute value. Well, here we have a complex exponential, e to the I times something, that is equal to 1 in absolute value. And we're focused on the interior of a domain. Little r is strictly less than capital R. So this does satisfy the requirement for a convergent geometric series. Although convergence would be quite slow if you have a point that's close to the boundary. But in any case, geometric series is something we have a formula for the exact sum of. You would have learned in Cal 3. So that's what I filled in here. So the sum of geometric series is equal to its first term, which is what you get for, now notice n starts at 1 here, over 1 minus the expressions being raised to the nth power that we see here. And similar for the other sum. So now there are no more summations. Everything's in closed form. So that's one advantage of taking this approach, that we can get rid of the summations. We still have a pretty nasty expression here, though. Let's see what we can do with that. First, to clean up a little bit, I'm going to multiply top and bottom by capital R. Gets rid of some pesky denominators. And then put everything here over a common denominator. And that leads to some simplification. We get rid of complex exponentials in the denominator. In fact, we can, let's see. Like here we have e to the I theta minus alpha, and here we have e to the minus I theta minus alpha. So this times this will cancel in this term. And then here we'll still have e to the I theta minus alpha and e to the minus I theta minus alpha. But the sum of those two is going to give us 2 times cosine. So again, so now our entire expression is real again. And of course, we expect the expression to be real because that is what we started with. But we'll try to get it in that form without any summations. And it turns out we're able to do so. And then we have this plus 1 sitting out here. So if we include this instruction, put everything over a common denominator, then in fact it actually simplifies even further. And now we have this. So now our solution u of our theta is this integral of this expression times our boundary data. So you can think of this as being like a kernel. So this is called the Poisson integral formula for a solution of the interior Dirichlet problem. Now chances are the integral would need to be evaluated numerically. So at least not having to evaluate an infinite series. So suppose you were to evaluate this formula at the origin. Well, that means little r equals 0. When that happens, okay, so that's gone. All these terms are gone. So this fraction collapses to 1. And you get this. But this is equal to the average value of g all along the boundary. Which makes sense because u is a solution of Laplace's equation. A function for which Laplacian is 0 is equal to the the average of its values so the value at a point for the solution of the Poisson equation, also known as a harmonic function, is equal to the average value of any circle with that point at its center. So based on what I showed you last time about the relationship between the value of the relation of the value of a function at a certain point to certain averages in terms of the Laplacian, this is what would be expected. This expression in the denominator, you might recognize this. It's coming from the law of cosines that you learned about in trigonometry. That this is the square of the length of the third side of a triangle. So if you have a triangle with side lengths little r and capital R, and the angle between those sides is in this case theta minus alpha, then this expression gives you the length of the third side. All right. Okay. Now, if you have a Laplace equation defined on a non-circular domain, you can use what's called conformal mapping, which is covered, for instance, in complex analysis courses, to map your domain to a circle, and then apply Poisson's integral formula, and then transform back to the original domain. Because that would preserve Laplacian. So here's an example of a Dirichlet problem. So we're solving Laplace's equation on a unit disk. So capital R tilde would be equal to 1 in this case. And here's our boundary data. So on the boundary, the unit circle expresses a function of theta, sine theta minus sine 2 theta. Here's a solution formula that I put up before. Now I fill in the particulars. So R tilde is equal to 1 in this case because we're on a unit circle. And then the coefficients, an and bn, are the Fourier series coefficients of our boundary data, sine theta minus sine 2 theta. Now those coefficients aren't given by these integral formulas, but in this case, given the form of g of theta, we don't need to use those because we have orthogonality of sine and cosine. So because our boundary data is a linear combination of sines, there is no component in the direction of any cosine. So all of the an will be 0. So so G is orthogonal to all cosines. As for the bn's, for B1, we have a coefficient of sine theta, which is 1. And then for B2, we have a coefficient of sine 2 theta, which is -1. There are no other signs here, so all other BNs will be 0. So we're just going to have these two terms, and what ends up happening, if you compare our solution with the boundary data, it has the same form. The only thing that's happened is that we have the appropriate powers of R multiplying each term. So for sine 1 times theta, we have R to the first power, and for sine 2 theta, we have multiplied by R squared. So that's what would happen in general. That if you have initial boundary data in this form, you could just stick in the appropriate factors of R. Now, keep in mind, if you're on a circle whose radius is not 1, don't forget to divide by the appropriate power of your radius. But yeah, so this gives you a shortcut on top of a shortcut. For boundary data of this form, if you figure out the right factors, if you have the correct powers of R and the correct scaling factors, if need be, you can jump directly to this. Solve this kind of problem lickety split. Okay. So, any questions about what we've seen here? Or about any homework problems? We have a lot of people attending online today, so feel free to shout out any question or type it in the chat. I was just looking at what else I have to cover. As I mentioned, two other types of Dirichlet problems, one on an annulus and also an exterior Dirichlet problem. I thought, I wonder if I could cover those real quick, but my notes there are a little bit more extensive. Okay. Actually, I think what I will do is go halfway with it. also work. Okay, so this is where I just left off. So I've been talking today all about the interior Dirichlet problem, where the solution must satisfy a PDE, Laplace equation, the inside of the circle. What about outside a circle? So here, for example, it's already expressed in polar coordinates. This is Laplace's equation. And for your radial variable, greater than 1. So this is outside the unit circle. Same boundary condition. Specified on the circle. And I'm throwing this in, well, first of all, because I still have a lot of time today, but also the solution process for the exterior problem is extremely similar to that of the interior. So, when you were solving, if I go back to what I was showing you before, okay. Hold on a second. All right. So before I mentioned this general solution, but I should mention that I've left out a solution here. There's one more that we're pointing out. If you prescribe that n is 0, then okay. Then there's more solutions possible. Okay, so these apply for more general n. Well, actually, if n is 0, then this case is covered. So actually, that's kind of redundant. That's redundant. So let's toss it. Okay. So if n is 0, then we have little r squared r double prime plus little r prime equals 0 as our ODE. Of course, the derivative of natural log of r is 1 over r. And then, if I take the second derivative, I'm going to get minus 1 over r squared. So if I substitute natural log of r in here, ignoring this because n is 0 anyway, it will satisfy. Now, for the interior Dirichlet problem, I still needed to exclude this because this is undefined at the origin. But the exterior Dirichlet problem, we're not dealing with the origin, so this is a solution that we should account for. Okay. So we exclude that solution for the interior case, but for the exterior case, we also exclude it. Okay. Here for a different reason. So So I did need to point out that natural log of r is a solution. It does satisfy Euler's equation. It's just that for interior exterior we never use it. For the interior problem, like I said, we cannot include any solution that blows up at r equals 0. For the exterior case, we need to toss out solutions that go to infinity as r goes to infinity. The reason why is that would never be a physical reasonable solution. We do not have physical phenomena that blows up like that. That would be a huge problem. So for r and cosine n theta, r and sine n theta, when we have positive exponents, those would be unbounded as r goes to infinity, so we can't include them. Natural log of r is a function that grows slowly as r goes to infinity, but it does grow, it does become infinite, just at a slow rate. So that also has to be excluded. So here's our solution formula now. And notice it looks exactly like one for the interior problem, except now we have an exponent of minus n. And then we have the same formulas for a and b n for satisfying the boundary data. So the a and the b are the Fourier series coefficients of G. And then if we have the boundary being a circle of radius capital R instead of at 1, so really this is more general. I recommend dealing with this one. So as an example, solving Laplace's equation on the entire two-dimensional space, excluding the unit disk, so little r is greater than 1. Here's our boundary condition. Then, to jump quickly to the solution, all we have to do is identify the value of n that goes with each term. So here, constant factors, n equals 0. Sine theta, that's n equals 1. Cosine 3 theta, that's for n equals 3. So, for each of these terms, we multiply them by r to the minus n for the appropriate value of n. So r to the 0, r to the minus 1, r to the minus 3. Done. So this works for the exterior Dirichlet problem, where you have use exponents of minus n. And it works for the interior Dirichlet problem, the exponents of n. So same approach. This is the appropriate sign. Yeah.
How do you tell if there's the difference between like an exterior and an interior then?
Oh. So in polar coordinates, where'd it go? Based on r. Here r is greater than some value. Okay. And this constant value r is where the boundary happens. Now that's the problem that's already described in polar coordinates. If in Cartesian coordinates, here we know it's interior because x plus y squared is less than something, as opposed to greater than something for exterior. And the only problem I have left to cover is Dirichlet problem between two circles. Okay, I'm looking at my notes for that. There's a bit more involved. For one thing, so whereas for the interior and exterior problem, I had to exclude the solution natural log of r for Euler's equation for because one case we have a concern in zero, for every case we have a concern in infinity. Neither one of those applies for the prominent annulus, so that solution is included. There's also a bit more work involved to find the correct coefficients, the counterparts to A and B, and we have more on that. So, all right, I think I will still hold off on that until Monday. Just because I wouldn't want to try to squeeze that into 20 minutes. But I do want to make sure if there are any other, check over any other questions. All right, so it's on a similar short class. Well, I guess a lot of these classes have been short, but certainly that will be true on Monday. And then, well, if I have something to say about the practice that's for the final exam, then I'll be able to talk about that too. Okay.